Okay, so before we start the problem solving session, let's just recap a little bit about inversion. So inversion is where you choose a circle, a fixed circle on the plane, and then you apply a transformation on the 2D plane. So it's just the same, it's like the same kind of transformation where you maybe translate by a vector, or you enlarge, or you rotate. These are all transformations, and inversion is just another transformation. It's where every single point on the plane will be mapped to another point on the plane such that the center of the circle, the first point, and the new point are on the same what we call same ray, because it's always in this direction. And that OP times OP prime is r squared, where r is the radius of the fixed circle. So that's inversion. It's kind of like reflection, but then your mirror is now a circular surface. If it's 3D, then it's a spherical surface. Okay, so inversion is just reflection across a circular mirror. And a few properties that we must remember, which is, first of all, the closer you get to the center, the further your reflection is. And in fact, it goes to infinity when you approach O. So when you approach O, the image of that point would be the point at infinity. So that's, well, one of the properties. And the most important properties is that lines, well, they say they preserve the set of objects that are consisting of circles and lines. So I'll just call them clines. So circles and lines. So if it's a circle, the image of the circle will be another circle. Okay, so if this is omega, then this is omega prime. And if it's a circle through the center, if it's a circle through the center of the circle, then the image will be a line. Oh, hang on, it will be this line. Okay. So hopefully you guys still remember this from a few hours ago. What else? Yeah, that's probably it. So remember, we only talk about circles and lines. They don't work on other shapes. Like if you have a random shape like that, you have a shape like this, then your image would be something like, probably like this. Yeah, but so it will be distorted, and therefore we only look at circles and lines. Okay, so that's inversion, and we're going to do some problem solving using this technique. So let's go to the first problem. We have a triangle ABC, and point D is inside the triangle. Now we draw three circles, B, D, and C. That. Like that, and like that, and like that. Okay, now from AD, we hit the circle again at A prime, BD, hits the circle again at B prime, and CD hits this circle at C prime. Then we want to prove that AD over AA prime plus BD over BB prime plus CD over CC prime is 1. Okay, we probably need to use the distance formula for inversion, which I didn't talk about just now, but you can refer back to the notes that Nelson gave, well, a few hours back. Okay, so I'll give you guys 20 minutes to try on this problem, and we will return at 3:01. Okay, so good luck. You can ask any questions in the meantime, and I'll try to answer. Okay, so anyone has any progress? Any idea on how to transform this equation? Or let's say transform the left-hand side into something else. So AD over AA prime. Can we write that as something nicer? Okay, so the trick about inversion is that, remember, if you have many circles going through a single point, right? If you have many circles going through a single point, then if you invert with respect to some fixed circle centered at this intersection point, every single, well, all three of the circles become lines, right? All three of the circles will become lines. Because remember, circles passing through the origin will be transformed to lines. And we exactly have this configuration where we have three circles. And, well, in fact, we don't even have to consider the line AB, AC, and BC. We just have to consider them as points. So what matters is the three circles. And we're going to do an inversion. Okay. So I'm not going to overlap the inverted image onto the same diagram, otherwise it will be extremely disgusting and ugly. So I'm just going to draw a new diagram representing the inverted image. So what we're going to do is we're just going to draw a perfect circle. You're just going to invert with respect to some fixed circle centered at D. It doesn't matter what the radius is. Well, you can just say it's a unit radius circle, a unit circle. Then the inverted image, I'll just zoom in here. So the inverted image, invert well, A prime, oh sorry, A goes to some other point, let's say A0. So by the way, I will denote any point X as inverted image X naught. So B goes to B naught and C goes to C naught. We don't care where it is, we just know it's somewhere. We cannot be sure that A naught, B naught, C naught is similar to A, B, C, and it normally isn't. But it's just 3 points. Okay. So now can anyone tell me what this circle, well, gives? I mean, what's its image under inversion? The circle BCA prime D. What's the image of that circle? Is the chat working? It's like very quiet. Oh, hang on. Oh wait, yeah, my chat is not working. That's why. Okay. Oops. Yeah. So sorry, I didn't see the chat just now. So the circle BCA prime. Well, first of all, we know it goes to a line. So we just have to see 2 points, like 2 reference points, to just know where the line is. So B gets inverted to B naught, C gets inverted to C naught. The circle passes through B and C. That means the image must also pass through B naught and C naught. And we know it's a line, so it's just this line. And similarly, we have this line. We have this line and this line probably. Yeah, I can't draw it properly. Hang on. C naught, B naught, C naught. Okay. Okay. Well, that's good and everything, but we're talking about lengths here. Oh, I deleted the problem statement. But we want to look at AD over AA prime. So, okay, first of all, what's the center of this blue circle after the inverted image? Is it D naught or is it something else? I mean, this is just a very minor detail. It's not going to affect the solution in any way. But what's the image of D and what's this point here? Okay, basically this is, well, the image of the point at infinity, right? So technically you can say it's infinity naught, which looks weird, but so I just, well, it's ugly, so I just call it O. So now, what's AD in terms of the lengths in the new diagram here? What's AD? Like AD in this diagram. What can I write it in terms of length in this diagram? So remember, OA naught times, well, it's still the same point D as well, but sorry, yeah, just D as well, but it's also the point, the image of the point of infinity. So dA naught times dA is R squared, right? But we just, without loss of generality, said the blue circle has radius 1. So let's say it's equal to 1. That means dA is just the reciprocal of dA naught. So that's nice. So that's one of the information we have. But how about AA prime? How about AA prime? First of all, we haven't talked about where A prime went. So where does A prime go? What's the image of A prime? Anyone? A point on B naught, C naught, yes. And which point exactly? How do I draw it out? So why isn't it here or here or here or here? Like which point is it? The intersection of A prime and BC. Yeah, exactly. So, or in, well, using the labels in this new diagram, it's the intersection of A naught D and B naught C naught. Sorry, it's not intersection of A prime and BC. It should be the intersection of A prime and B naught C naught, because now B naught C naught is a new line. Like if I want to draw this overlapping onto this, B naught is probably here, C naught is probably here, and then B naught C naught is this line here. But I'm not going to do that. I'm just going to draw a new diagram. So it's this point. Why? Because, well, the line AD prime, the line AD prime is a line passing through D, which is the center of inversion, and hence it will remain constant. I mean, like the line is fixed. So that line doesn't change. The line intersects the circle BCA prime at A prime. So we just look at the intersection relation, and we see that this line must also hit B naught C naught at A, well, at the image of A prime. Okay, so now we have this point here. How can we write A prime in terms of A naught and A naught prime? A prime naught. So there's a distance formula in the notes. There's a distance formula in the notes, but this is a simple case, and you can actually do it by basic definitions instead of using the distance formula. You can use a different distance formula if you want, but AA prime is just dA plus dA prime. dA is 1 over dA naught. What's dA? dA prime. It's going to be 1 over dA naught prime, right? Okay. So the final question, what's AD over AA prime? It's going to be 1 over dA naught plus over 1 over dA naught plus 1 over dA prime naught, and that is dA naught prime over dA naught prime plus dA naught, which is A naught prime. So we have this new, well, we transform the problem into the sum of dA naught prime over A naught prime, which is the green length over the blue length, right? The green length over the blue length. So how does this simplify the problem? Well, first of all, there are no more circles anymore. We don't have to worry about that. Now it's just a bunch of triangles and lengths. And y is in the translated problem. Why is it true that, I'm just going to relabel everything so I just don't have to say not every time. Oh, x prime, y prime, z prime, capital Z, sorry. Why is it that OX prime over XX prime plus OY prime over YY prime plus OZ prime over ZZ prime? Why is it always equal to 1? So that's the problem that we have translated it into after inversion. So any idea? OX prime and XX prime. But at this point, you can use trigonometry and bash it out, but there's a clean solution to this. Looks like Siva. Yes, it does a little bit look like Siva. Well, minor laws probably, but again, you don't need the minor laws to do this, to prove this. There's a very simple argument of why this is true. OX prime over XX prime over equals OYZ over XY. Yes, exactly. So it's about areas. It's about areas. So remember, if you have, well, if you have two triangles like that, or even maybe two triangles like this, well, I'll try to write this, PQRS. Then PT over RT is just the area of PQS over the area of RQS, right? Because they have the same height and the same base. You can analyze it that way. So what's this equivalent to? This is equal to OYZ over XYZ. This is equal to OXZ over XYZ. And yeah, so you get the other term. And why are these three terms why do these three terms sum up to 1? Well, it's obvious because you're adding this area plus this area plus this area. And they must equal to the whole area. So yeah, then we're done. So without inversion, it might be very, very difficult because, well, maybe not that difficult because it's a very simple diagram. You can probably bash it out using trigonometry at the first place. But applying inversion to this configuration, you transform the circles into lines, which simplifies your working. You're now analyzing, well, a diagram without any curves. Well, ignore the blue circle. The blue circle technically has nothing to do with what we're proving anyway. So, well, a diagram without circles is always better because if you're really stuck, you can just resort to some analytic techniques. You can probably change this into a graph or something because lines are easy, but circles are hard. Circles are quadratic, lines are linear. So the first step here is to change them into lines and then, well, use any way to finish the proof. In this case, I will just use the area method. Okay, so that's the first problem. Let's look at the next problem. So the next problem is, give me a moment. So the next problem, yeah, this one. We have a triangle ABC with, in fact, let me draw it. We have a circumcircle, we have a triangle, like that, ABC, circumcircle gamma. The internal angle bisector of angle A intersects BC at D, so D, and gamma again at E. The circle with diameter DE, oh, it's going to be quite hard to draw. Yeah, probably something like that. So this circle with diameter DE will meet gamma again at F. Prove that AF is the symmedian of the triangle. Is a symmedian, sorry. There are three symmedians in a triangle. So a symmedian, if anyone's not aware, is the reflection of the median over the angle bisector. Right, so if this is the median is the line connecting a vertex with its opposite midpoint. This is a median. If you reflect it across the angle bisector, that means you take the isogonal line, that's a technical term, then this line is called a semedian. Is the line symmetric to the median? So I want to prove that AF is the A semedian in this case, which is the semedian connecting A. So there are, okay, so you can try this proof, and the beginners can also try it as well, because this problem is not required to use inversion, but you can use inversion to simplify it. Okay, so again, I'll give, well, maybe this time 15 minutes. So we will return at 15:45 Malaysia time. Okay. Okay, so I've received a few responses. They are very good responses. So one of them is to, well, to create this point G here, right? So this is D, and then this is G, which is the second intersection point of the circle with diameter DE and BC. So first of all, G is the midpoint. Why? Because, well, G is the midpoint of BC. Why? Because first of all, from the usual properties of a circle, if we have two angles the same, then these two must be equal, right? Therefore, BE is equals to EC. BE is equals to EC. And if we draw GE, then GE is perpendicular to DG, because DE is the diameter of that circle. But since this is an isosceles triangle, that means G is the midpoint of BC, right? So that's good, very good. So first we know that we let DE intersect BC again at G. Then EG is perpendicular to BC, and hence G is the midpoint of BC. Okay, but what's next? We still have to use the fact that F is the second intersection, and we want to prove that AF is the semedian. So now we just have to prove that AF and AG are, well, symmetric over the line AE. So how do we do that? So there's a non-inversion way and an inversion way. And the non-inversion way is to draw, well, is to extend GE until we reach here. Let's say this is K, right? Then KE is the diameter by symmetry, right? KE is the diameter of ABC, because it's the perpendicular bisector of BC. Therefore, AK is perpendicular to AE, right? And now we are we done? No. So first of all, what's the property of F? Anyone saw any properties of F after I constructed K? Anyone found anything about F in this diagram? And it's something to do with K. KFE is 90 degrees, yep. And therefore, KDF, collinear, you mean? Yeah, they are collinear. Yep. Okay, so it passes through D. Because DFE is 90, which is also KFE. And therefore they are collinear. So KFE is collinear, or they colline. Then, well, that's nice because now we can create what I like to call a butterfly, which might be confusing. So in a circle, these two are always the same. And hence, wow, I need to draw this maybe here. Nah, still need to draw that somewhere. Okay, hence, wait, let's draw this line, AF. AF. And let's draw the line AG. AKDG cyclic, yeah. So DAK is equal to DGK is equal to 90. So AKGD is cyclic. What else? Well, now we can angle chase. Because this angle, the green angle, is equal to this angle. Right? Yeah, FKE equals FAE. But the same angle, the blue angle, is also equal to this by the consequentity, the cyclicity of DGKA. Yeah, so these two are symmetric. So yeah, the key here, if you don't want to use induction, to use inversion, is to construct this point K. Why? Because K connects quite a lot of things together. It connects the concept of F being that second intersection, and it also connects the midpoint G. So they link two concepts together, so you can find some results via the construction of K. BAF, yeah, we pretty much got it already. Yeah. Okay, but let's try inversion. And has Nelson in the lecture this morning talked about square root BC inversion? Did he talk about this thing, square root BC inversion? Okay, if not, then let's introduce this now. So square root BC inversion is a kind of inversion, but with an extra twist. So square root BC inversion is where, let me draw a nice diagram again. Okay, so here's what happens. Let me see if I can draw a dashed line. Probably not possible. So here's what square root BC inversion does. So what we do is to apply these two transformations in order. So first, inversion at A, centered at A, with radius square root AB times AC. So that's why it's called square root BC. Okay, I'll tell you why later. But anyway, after this inversion, we are going to reflect across the internal bisector internal angle bisector of angle A. So this is what we call square root BC inversion. So you invert at A with this radius, which is quite weird, but you'll see that it gives something nice, and then reflect across the internal bisector of angle A. So it's kind of like a reflection of the entire plane, right? So I reflect like that. Okay, what does it have? Oh, well, where does B and C go? Anyone has any idea? So where's the image of B? Where's the image of C? After I apply these two transformations. Yes, exactly. B and C swap, right? So that's why we pick the radius to be square root AB times AC. Because where does AB go? AB would go to a point such that AB times its image is equals to AB times AC squared, which is AB times AC. Anyway, that means that after the inversion, these two lengths are the same. These two lengths are the same, and then you swap, right? You reflect across the internal bisector of angle A, then B prime goes to C. So yes, oops. And therefore C goes back to, well, whatever that is, B. So I'll just let this transformation be called phi, because it looks fancy. So B would, well, phi B is C, and phi C is B. Okay, now where does line BC go? Where does line BC go? Is it BC? Remember what happens when you invert? What happens when you invert a line? It becomes a circle, right? It becomes a circle. And after, so let's think about this. Let's think this through. So a line, after this first transformation and inversion, it probably goes to a circle. Well, the only case where it becomes a line again is when it's passing through the center. But this line BC is not passing through A. So it becomes a circle. We don't care what the circle is. But then after you apply 2, it's still a circle. Therefore, after we apply this whole transformation phi, the line becomes a circle. So which circle, you might ask? So let's take a look at what circle it must be. Well, it must pass through the image of B, which is C. It must pass through the image of C, which is B. And after transformation 1, this circle must pass through A. After transformation 2, it remains to be passing through A. So it must be the circle ABC. It must be the circle ABC. Must be the circle ABC. And well, same thing. If we apply this to the circle ABC, we get back the line BC. So a bunch of nice properties here. Okay, but now let's apply this concept to the problem and see what we can find. Maybe I should redraw the diagram. Or I'll just copy and paste. So we don't want K anymore. We probably don't want G anymore as well. Oops. Okay. So let's see. Where does E go? This is D here. So let me ask. So where does AD go? I mean this line AD, or the line ADE of it as well. Where does the line, the whole line ADE go? D swaps with E. Okay, I was going to use this fact to show you that D swaps with E, but yeah, but also fine. If you can see why D and E swap, then yeah. So well, it's the same line ADE. And the simple reason is that after transformation 1, the inversion transformation, it remains the same line, because remember, if you invert a line that passes through the center of the inversion, the line stays still because everything is transformed within that line. It doesn't go anywhere else. And then you apply transformation 2, well, that line AD is exactly the internal bisector, so it's reflecting across itself, and therefore it doesn't change the location anyway. So after both transformations, you get back itself. So using these three, you can see by intersection, by looking at the intersections, that D and E swap. D and E swap. Because D is on BC, E is on the circle ABC, and you know that AD, AE, they are constant. So you look at how the shapes intersect, you can conclude that the image of D is E. Very good. Very good. But now, how about the circle with diameter DE? The circle with diameter DE, where is its image? So this one is a bit tricky because it doesn't use the concepts we learned, but it's a very simple observation if you notice it. So where does the circle with diameter DE get mapped to? The line DE, why is it? Well, it's definitely not a line because the image of the line is itself. And the circle is not this line, so it cannot be the line DE, right? Like if it were DE, that means it's the same thing as this, which means that these two are the same, which is not correct. Right? So what is it? So if you look at the points on it, A is here, D is here, E is here. After the transformation phi, which is the square BC inversion, D and E swap, right? D and E swap. So the resultant circle, the image of this circle, must also pass through D and E. Okay, so you might say it's exactly itself, which is correct, but I need to ask one more question. So why isn't it something like that? Maybe another circle that passes through D and E. Or why is it not like that? Why is it not anything else? Why is it exactly itself? DE passes through the center. Yeah, so it's symmetric, right? Yeah. Because if you look at these two things, the inversion, well, inversion is a very symmetric thing. It's a very centrally symmetric thing. So, and then the second one is the reflection across the internal bisector of angle A. This circle is itself symmetric across the internal bisector of angle A. Therefore, it goes to itself. Cannot be any other circle passing through D and E. So it's a very fun analysis. But now let's see what happens. So given all of this now, let's just introduce this as G again. Okay, never mind. Let's say, so what's F? What's the image of F? Okay, let's do this one by one. So F is the intersection between ABC and this thing. Okay, fine. It's not E. Not E. I don't know how to write this nicely, but it's not E. So it's the intersection between ABC and DE, which is not E. So this must be the image of ABC intersect the image of DE, okay, which is not the image of E, which is D. But what's the image of ABC? That's BC, line BC. What's the image of line D? Sorry, this is not a line. This is the circle with diameter DE. What's that? That's again the circle with diameter DE, which is not D. But that's G, right? That's the thing that we introduced in the last solution. And we already proved quite nicely that it is the midpoint of BC. Okay, so can anyone tell me why we're done already? So the image of F is G, but so what? How did it prove the statement? So recall what phi really is. Then F is a reflection of G over the angle bisector. Well, AF, the line AF is a reflection of the line AG over the angle bisector, yes. So yeah, so look back at the definitions of phi. So the image of F is G. So let's look at the line AF. So the line AF, I invert it, it's still the line AF. I reflect it, it must be something that passes through the image of F, which is G. So therefore AF and AG must be reflections across the internal bisector of angle A. So by 2, we are done. So this is what we call square BC inversion. So you must, when you do square BC inversion, you must remember that it's not just inversion. Okay, so that means you have to be careful because you might have the impulse to say, oh, the point is here, so the image must be there. But that only applies to a single application of one inversion. But here we have inversion, then reflection. So you must be careful when you're keeping track of the images of a particular point on the plane. Okay, but still some properties still apply. For example, if they intersect, then in the image, they also intersect. Well, I mean the shapes. And you can use what you learn from inversion to discover new properties of the square BC inversion transformation. Okay, if that's fine, and if you have a question, you can feel free to ask anytime. So if everyone's fine, then let's move on to the third problem. Let's move on to the third problem. So remember this trick. This trick is quite common, I must say. So let's clear this and then let's look at the next one. So again, we have circumcircle, we have triangle inside. is gamma. The circle omega is tangent to the sides AC and BC, and is internally tangent to the circle gamma at point P. So it's what we call a mixtilinear circle. Mixtilinear circle. Yeah, something like that. This is omega. So it is at the point P, tangent here. A line parallel to AB. Hang on, AC and BC, right? Sorry, this should be C, this should be A, this should be B. Parallel to AB, intersecting the interior of ABC, tangent to omega at Q. So it's this. Okay. So these two are parallel. It's tangent to this circle at Q. And you want to prove that ACP equals QCB. You want to again prove that CP and CQ are orthogonal. So yeah, a similar theme with the previous problem. You want to prove that these two are equal. So again, I will give you a few minutes to try. I'm not sure if we have time here. I'll give 15 minutes and then we will discuss in the last 5 minutes. So that would be 4:25 p.m. or 24. Okay, have fun. Okay, anyone, any idea? So here we want to prove that CP and CQ are orthogonal. They are the reflections across the angle bisector of angle C. So what might you be motivated to do as a first step? Anyone? So what I'm going to try to do is I will apply square root BC inversion again and see whether it tells us something. Because square root BC inversion has this step where we reflect across the angle bisector, right? So maybe P and Q has something to do with the images of each other or something like that. So let's see if we can analyze what happens when we apply phi. Again, I define phi to be the square root BC inversion, because you have to write that in your proof if you want to use that notation. So again, A and B, they are images of each other. Well, in this case, it's not square root BC, it's square root AB, but you get the point probably. Okay, then What else? AC, sorry, CA, the line CA and the line CB must also swap. Anything else? Okay, remember CAB gets to be AB after the transformation. Okay, now what can we say about omega? What can we say about omega? First of all, omega is tangent to AC and BC. That means its image must also be tangent to BC and AC. Well, it's the same two lines, but I phrased it the other way around because I want you to know that it's the images of those lines. So it must be tangent to those lines as well. And it must be tangent to the image of the circle, the circumcircle, which is now the line AB. So this is tangent to AB, CA, and CB. So yes, very good point. It might be the in-center, right? But there's also one more circle that obeys these three properties. Tangent to AB, CA, CB. Actually, there are four circles, right? They can be the in circles, they can be the X circles as well. So we have to make sure we know which one it gets mapped to. So what can it be? What must it be? Can it be the in circle? Well, first of all, it cannot be the B or AX circles because those are in the wrong directions completely. So it's either the CX circle or the in circle, right? But if it's the in circle, if I do that whatever square BC inversion, can it become omega? That's the question. Because the circle with radius square root AB is something like that, right? Something like that. If I invert omega, where will it go to? It will go outside of that circle, right? It will go outside of the circle and it cannot be omega anymore. That means, well, that means it cannot be the, what's it again? The in circle. It must be the X circle. It must be the X circle. I hope that makes sense. Because there's a huge part of omega that's inside this portion, it's inside the triangle, which cannot be the case. That means we have to draw the X circle. It's probably something like that. Let me hang on. I cannot draw this nicely, but you probably get the point. So it must be that. Okay. So this is the CX circle. The CX circle. Now, how can we use that fact? Well, now omega and this CX circle is a homotety, right? It's an enlargement from C. Right? Homotety means enlargement from a point. In that case, we know that if we extend Q by similarity, it must also hit the tangent point, which is somewhere here. So Q prime. Probably I shouldn't write Q. Okay, fine, just put Q prime. So CQ, Q prime are collinear, and Q prime is a tangent point. Because it's tangent here, it must be tangent here as well, because it's an enlargement. Okay. Now what can we say? Where's P? Where does P go to? P is tangent to the, well, P itself is a tangential point of ABC and omega. So the image of P must be the image of omega and the image of ABC, which is the CX circle intersect line BC, which is Q prime, and we're done, right? So P and Q are images. So sadly, it's not P and Q that are images of each other, but rather this new point Q prime, which is, well, it lies on CQ anyway, so it doesn't make a difference. So therefore, the image of P is Q prime. That means CP and CQ prime, and hence CQ are isogonal. They are reflections across the angle bisector of C. Okay. So any other questions before we end the lecture, the problem solving session? So if you want some challenge, you can try the next few problems, the next 3 problems. And well, or you can find some other problems online and try just to familiarize yourself with this technique, because it will be significantly more important as you move on to the harder problems in geometry. Why is phi omega tangent to AB? Good question. So omega itself is tangent to omega is tangent to the circumcircle ABC. That means that images must be tangent as well. But what's the image of ABC? The image of ABC is AB. So the images must be tangent. That means phi omega must be tangent to the line AB. Does that make sense? May I know why it does not reflect at angle bisector of C? It does. It does reflect. Okay, I get your point. So you mean omega and the CX circle, right? Well, actually they do. It's just that after you reflect, it remains the same thing, because, well, these 2 circles are symmetric across the angle bisector anyway. They are tangent to AB and AC. CA and CB. So it's if you draw like it's like a kite. Well, it's not a kite, but basically they're symmetric across the angle bisector anyway. So if you do that reflection, it remains at the same place. How about Q prime? Well, yeah, they do. Like after you invert P, it should be somewhere here. And then you reflect, you get back to Q prime.